My name is Robert Golden, and I, along with my fellow group members, Ibrahim Boutros, Jared Jordan, and Kevin Ogle, are here to discuss and educate the class on structural lightweight aggregate concrete. Lightweight aggregate concrete is a specialized type of concrete that replaces traditional heavy aggregates with lightweight materials like expanded shale, clay, or slate. This substitution results in a concrete that is 20 to 40% lighter than standard mixes, which significantly reduces the dead load on structures. While normal concrete weighs an average of 150 pounds per cubic foot, lightweight aggregate concrete can average anywhere between 90 and 115 pounds per cubic foot. The concept of using lightweight aggregates dates back to the earliest 20th century, with practical applications beginning in the 1920s and 30s, primarily to address challenges in constructing taller buildings where weight reduction is critical. Over time, advancements in both aggregate production and concrete technology have enhanced the reliability and performance. Today, it is a trusted solution when weight savings translate into cost and design benefits. There are both engineering and economic factors motivating designers and engineers to incorporate lightweight aggregate concrete into their projects. From an engineering perspective, lightweight aggregate concrete reduces dead loads, which allows for longer structural spans, smaller foundations, less steel reinforcement, and even improves seismic resilience. Economically, it offers direct cost savings by reducing material and labor expenses. Additionally, faster construction timelines help to decrease the costs associated with cranes and other heavy equipment. Another important economic advantage is the potential for increased revenue by maximizing the usable floor space and optimizing framing designs, making projects more efficient and profitable. Lightweight aggregate concrete has significant real-time applications in three major areas: high-rise buildings, bridge and marine structures, and precast and pre-stressed systems. For high-rise buildings, lightweight aggregate concrete helps minimize the size and load on columns, beams, and foundations, which is crucial for upper floors. In bridge and marine structures, it reduces the weight on girders and other precast elements, enabling faster construction and longer spans. Precast and pre-stressed systems benefit from these innovations by requiring smaller cranes and lifting equipment to handle components, contributing to the expansion of tilt-up construction. Overall, these applications demonstrate how modern engineering techniques, such as lightweight aggregate concrete, can help improve efficiency, safety, and performance across various construction types. One Shell Plaza, located in Houston, Texas, and originally built in 1971, is a perfect example of how lightweight aggregate concrete can positively impact a project. The original design was limited to 35 stories due to size constraints on the foundation and soil conditions. By incorporating lightweight aggregate concrete, engineers were able to increase the building height to 50 stories without changing the footprint of the foundation. This advancement not only resolved the structural limitations of the project, but also resulted in a 40% increase of usable and rentable space, demonstrating how material innovation can significantly enhance building capacity and economic value. Another real-world example of the successful use of lightweight aggregate concrete is the Tacoma Narrows Bridge located in Tacoma, Washington. The bridge was originally built in 1950 and underwent a significant deck widening project in 2007. The use of lightweight aggregate concrete in the deck expansion allowed the bridge to expand from 4 to 6 lanes, increasing traffic capacity by 50%, without the need for major structural upgrades to the piers or footings. The bridge maintained its seismic resilience post-expansion, despite the expanded capacity and lack of major structural modification, and set a precedent for using lightweight aggregate concrete in seismic retrofits nationwide. Again, demonstrating how innovative materials and techniques can effectively extend the life and functionality of existing infrastructure while ensuring safety and performance under seismic conditions. Here are a few more examples of projects that highlight the innovative use of lightweight aggregate concrete across the United States. First is One World Trade Center in New York, where lightweight aggregate concrete was utilized in the upper floors to reduce the structural load, allowing for a taller, more resilient design without compromising safety. Next, the San Francisco-Oakland Bay Bridge in San Francisco, where engineers incorporated lightweight aggregate concrete into portions of the bridge deck and supporting structures to enhance seismic performance while minimizing overall weight. And finally, the Marina City Towers in Chicago. The unique cylindrical towers benefited from lightweight aggregate concrete to achieve their slender profiles, improving efficiency in both material usage and construction methods. Again, these examples demonstrate how lightweight aggregate concrete enables architects and engineers to push boundaries in structural design, sustainability, and safety.
Hello, my name is Jared Jordan. We know that now structural lightweight aggregate concrete is successful, but what are some of the governing bodies that manage the design constraints and performance requirements so that it meets these successes? ASTM, there are two that cover structural lightweight aggregate concrete. There's ASTM C330, which is the standard specification for lightweight aggregates for structural concrete. This governs the lightweight aggregate that makes SLWAC so important and so successful. ASTM C567 is the standard test method for determining the density of this aggregate. And then lastly, there is ACI 213R, which is a fairly condensed but very comprehensive guide on placing, proportioning, mixing, basically almost everything you need to know. ASTM C330/330M-14 is what governs the aggregate going into structural lightweight concrete. It covers two general types, aggregates that are prepared by being pelletized, expanded, or sintered, such as blast furnace slag and fly ash. It also covers clay, shale, things like that. It also covers aggregates prepared from natural sources. This can be pumice, tuff, scoria, things like that. The ASTM also very clearly states that all of the lightweight aggregates need to be composed predominantly of lightweight cellular and granular inorganic material. This is very important. They will also be tested. They won't contain excessive amounts of deleterious substances, outside things. ASTM C567 is the standard test method for determining density of structural lightweight concrete. It is used to find the equilibrium density of the concrete, but in order to actually perform the test, you need to do all of the other ASTM tests on your concrete. C138, the bucket density, 192, making strength specimens. Basically, anything you would do when testing standard concrete, you have to do that first. Then you would take either, there's two ways to determine it. You can do it from the test specimens you made, your strength cylinders, or if you have a batch with known mixture quantities, aggregate moisture content, and the volume of the concrete batch. You could use the equation shown here and then go down to section 9.2 and calculate your approximate equilibrium density. Using the test specimens, it involves curing them in water, measuring them in water, measuring them suspended. And now that we know how to find the density of structural lightweight aggregate concrete, we can compare it to standard weight concrete. It is typically significantly less dense than your standard weight concrete. It has a density ranging from about 100 to 115 pounds per cubic foot. You can compare this to standard weight concrete, and it's a staggering difference. It's almost, in some instances, 55 pounds per cubic foot lighter than your standard weight concrete. This is achieved because the aggregates are very, very porous. You see we have an illustration here on the side. You get this aggregate to saturated surface dry, or SSD, and it's pretty much perfect. It's still, even saturated, it's still significantly lighter than a lot of your standard weight aggregates. Most mixes will use normal weight fines like sand, so standard weight sand, and then mix in a lightweight coarse aggregate. There are, however, many instances where they do both, and these can be very, very lightweight mixes. Well, they use a lightweight fine and a lightweight coarse. Though it has a significantly lower density than standard weight concrete, standard lightweight aggregate concrete does not have lower strengths. Many have a 28-day design strength of 2,900 to 5,000 psi. In instances where you need a higher strength application, They can also go up to at least 10,000 psi or more if necessary. The primary limiting factor for lightweight aggregate concrete is the lightweight aggregate itself, however. Standard concrete will fail through the cement paste matrix, but with lightweight aggregate concrete, I should say, it will fail through the lightweight aggregate. This is because the cement paste and the lightweight aggregates, their stiffness is so similar, it'll go through the lightweight. I've mentioned the porosity of the aggregate a few times now, and it actually plays into how you mix your concrete as well. Um, the porosity of the lightweight aggregate means that it could absorb anywhere from 5 to even 20% of its dry weight in a 24-hour absorption period. Um, it is very, very important that this aggregate is saturated prior to batching, because what will happen is if you do not do this, it will want to absorb a lot of your mixing water that you're throwing in while batching. If it does this, it will throw off your water cement ratio significantly and can make a very, very bad mix. Um, to prevent this, we pre-wet aggregate. Many ag bins have sprinkler systems set up on them. Uh, they will dump water on them. They'll leave them out in the rain. Uh, Pre-wetting is very, very key to making sure that structural lightweight aggregate concrete is successful. Uh, when it is successful, uh, it has many applications in severe marine environments. They've done a number of studies where it's performed extremely well because of the thaw performance, the freeze performance. In many cases, it is equal to or exceeds the durability of standard concrete.
Hello everyone, my name is Ibram Butros, and in this section I'll be talking about the difference between structural lightweight aggregate concrete and normal weight concrete. On this slide, the main focus is the structural lightweight aggregate concrete reduces dead load while it's still maintaining strong mechanical performance. Even though it's lighter concrete, it still shows the same strength and long-term behavior as normal weight concrete. This makes it practical option in structures where weight savings matters in multi-stories or long span applications. Structural lightweight aggregate concrete typically achieves between 28 to 40 MPa in a comprehensive strength depending on its mix. This means that the lightweight concrete can actually equal or sometimes be stronger than normal weight concrete. Because of this, engineers are confident when saying using structural lightweight aggregate concrete is good in high-rise structures when reducing a dead load can significantly lower the demand of foundations and framing systems. On this slide, we see that the structural lightweight aggregate concrete has slightly lower tensile and flexural strength. This is mainly just because the properties of the lightweight aggregates are not as stiff as normal or natural stone aggregates. The reduced weight on the structural lightweight concrete can actually help reduce cracking risks during construction. In practice, reinforcement design easily compensates for a lower tensile capacity, so structural performance is still reliable from the lightweight concrete. One of the biggest mechanical differences between structural lightweight concrete and normal weight concrete is the lower modules of elasticity. This means the structural lightweight concrete deforms more under load. This is not necessarily a disadvantage. Engineers simply account for it by adjusting member size or reinforcements. As long as the design considers this lower stiffness, structural lightweight concrete still performs well in applications. When talking about durability, structural lightweight concrete performs significantly well. When the mix is properly designed, lightweight concrete has an excellent freeze and thaw resistance, which is important in colder climates. Its resistance to chloride penetration is also comparable to normal weight concrete. This makes the structural lightweight concrete suitable for buildings like the marine structures, bridge decks, and environment exposed to any de-icing salts. lightweight aggregates do have a higher absorption, which increases water demand in the mix. Because of this, pre-wetting the aggregates is a common technique to keep the structure or the mixture more stable. Long-term studies show that when mix design and curing are done correctly, structural lightweight concrete performs consistently over time and maintains a good durability. Structural lightweight concrete reduces dead load, maintains a strong comprehensive performance, and offers reliable durability. When engineered correctly, it's lightweight and a structurally solid alternative to normal concrete.
Providing a limitations framework. In this final section, I'll focus on the primary limitations that engineers must consider when using structural lightweight concrete. Earlier slides cover what the material is and where it performs well. Now we shift to the practical constraints that influence design decisions. These include cost, workability concerns, placement challenges, mechanical behavior, durability issues, and a level of field quality control required. Understanding these factors helps balance cost limitations. One of the most significant limitations relates to cost. Lightweight aggregates such as expanded shale, clay, and slate are more expensive due to their specialized reduction and handling. In some cases, they cost 30 to 50% more than traditional materials. These expenses may be justified when reducing structural weight leads to savings in foundations or reinforcement, but for budget-driven projects, workability and mixing challenges. The material's high absorption rate creates challenges during mixing. Lightweight aggregates can draw water rapidly from a mixture, causing slump loss and inconsistent workability if not managed carefully. Pre-wetting the aggregates and monitoring moisture levels are essential to maintain the intended performance. Without this attention, the concrete pumping and placement restrictions. Another limitation involves placement. Because lightweight aggregates are more fragile, they can fracture under high pumping pressures or through long delivery lines. When this happens, density and strength become inconsistent. Reducing pump pressures, shortening lines, or using alternate placement methods, such as mechanical behavior constraints. Lightweight mixtures typically have lower stiffness than conventional concrete, which leads to greater deflection under load. Although compressive strength can be comparable, serviceability often becomes a controlling factor. Designers may need to increase reinforcement or adjust member dimensions to keep the absorption and durability issues. Because the aggregates absorb more water, the material is more sensitive to shrinkage, permeability, and durability concerns if moisture isn't controlled. Improper handling can increase cracking or reduce performance in harsh environments. When pre-wetting, air entrainment, and proper curing are followed, durability remains strong. Absorption and durability issues. Because the aggregates absorb more water, the material is more sensitive to shrinkage, permeability, and durability concerns if moisture isn't controlled. Improper handling can increase cracking or reduce performance in harsh environments. When pre-wetting, air entrainment, and proper curing are followed, durability remains strong. Summary of limitations. In summary, the material offers meaningful advantages for reducing structural weight, but several limitations must be considered. Higher costs, moisture sensitivity, pumping restrictions, and mechanical differences all influence how it should be designed and placed. With proper planning, mix adjustments, and disciplined field control, lightweight concrete can remain.
In summary, structural lightweight aggregate concrete presents a practical solution for construction projects where minimizing weight without sacrificing structural integrity is crucial. Lightweight aggregate concrete is especially suited for applications such as the upper floors in high-rise buildings, bridge decks, marine structures, and precast systems. While the initial investment may be higher, these costs are often offset by long-term financial benefits, including reduced foundation requirements and easier transportation. Ensuring compliance with ASTM and ACI standards is essential, as rigorous testing confirms that materials and mix designs will deliver the expected performance. Additionally, proper handling and placement techniques are needed to guarantee that lightweight aggregate concrete reaches its targeted strength and durability, making it a reliable choice for demanding environments. Thank you.